Yeah.
And so yes, so the title that Bill came up with was How to Do Industrial Research, MRI at GE. So thank you very much for agreeing to talk.
Okay, thank you, Richard. And hopefully this will work. Let's see. Yes. Okay, so what I'm going to talk about is the early MRI at General Electric, which I participated in. And also I have a hypothesis about why it was very successful. So first of all, just to tell you, this was the GE Corporate Research Lab in Schenectady, New York. Technically, it's in a little suburb called Niskayuna, which is what they say now, it's in Niskayuna. And it has about 2,000 employees, and about 600 of them are PhDs. So this is pretty substantial. It's kind of like a university. And so they do a lot of things: chemistry, physics, biology. They think GE Healthcare bought, which one, the British company? Anyway, they have a lot of biology related to drug developments, and they did MRI, CT, and ultrasound, power engineering, metallurgy, and computer science. So it's really a wide-ranging thing. Okay, so the important things, what are the important ingredients of industrial research? Well, you have to have a good project. Well, MRI was like the winning the lottery of projects. It's like the project of the century because it was such a rich subject and it expanded so enormously. You need good management. Well, what does that mean? You need to empower your employees, and this is usually said by managers, but usually they don't do it because they are control freaks, and in this case they weren't. You need good researchers, whatever that means, but I think that has to include independence and curiosity, and you need freedom and responsibility for researchers. So the secret ingredient I'm going to talk about that really made this work was the participation of the researchers in the scientific enterprise through publication and conferences. And what I found was a lot of people at the R&D Center would say, oh, they don't let us publish, which might be partly true, but in reality, they didn't really want to publish. They didn't really want to go to the effort. Okay, so a couple of people you know here, myself and Paul Bottomley, and I'm an American, and people think, because I worked in Britain, some people think I'm British, but they don't hear my accent, I guess. So I was born in New York State, grew up in Chicago suburbs, went to the University of Illinois, got a PhD at Harvard. Then I went to Britain, where I looked for gravitational waves in Glasgow, and went to Aberdeen, where we worked on early MRI and developed spin warp. Paul Bottomley is Australian, unless he's faking the accent, and he went to Monash University, also in Melbourne, where he got his bachelor's degree, got a PhD in Nottingham, and then he came to Hopkins as a postdoc. And that was before he went to GE. So we both arrived in GE in about September of 1980. So what about the GE management? Well, the corporate management was, our immediate boss was called Red Reddington. His real name was Roland. Laddie Stahl, who is a former Army general. That was pretty interesting. Virgil Stout and Roland Schmidt, PhD in physics. So it turned out that these guys were actually kind of flexible. They didn't seem like it at first, but this was really, really important because things change rapidly. And one of the things that was interesting was, why was Reddington called Red? I mean, he didn't have red hair. He didn't really have any hair. And but that was a tradition. And there was actually a scientist from Thailand whose last name was Tantraporn, and he was known as Tan Tantraporn. And the best one was, this went back a long time, was William Coolidge, the inventor of the modern X-ray, was known as Cool Coolidge. So GE Medical Systems is the other part of this story. They're in Waukesha, Wisconsin, which, as you know, is 1,000 miles to the west. And Walt Robb, a PhD in chemical engineering, was in charge of that at the time. And he actually did his chemical engineering degree at the University of Illinois, along with Jack Welch. A few PhDs, Richard Kinzinger, and Lonnie Edelstein, Maury Blumenfeld, who were also PhDs. And the point I'm making here is that at this point, they had people who were really technically knowledgeable in doing stuff, important stuff. Okay, in 1980, Reddington and others had just finished a highly successful CT development, and they were interested in MRI, but medical system wouldn't give them money. So they said, okay, well, we don't think it's any good anyway, because it's not going to be as good as CT. So when I arrived, to my surprise, I was wondering, well, why did they hire me if it's no good? And he said, well, it's because the resolution of CT is 1/10 of a millimeter. So it turned out, when I inquired a bit more, it was 1/10 of a millimeter for a steel pin in a vacuum, okay? But that's not realistic, because in reality, you have different soft tissues which have very, very little contrast. So it turned out that when I did a calculation comparing MR and CT, that they were pretty comparable. So, but in the meantime, Medical Systems was doing great. They had developed this fan beam CT, and they didn't really have time for MR, so they didn't want to do it. So the plan at our place, the corporate research place, was using assessed money, which was a tax on all the businesses, buy a high-field supercon magnet, 2 Tesla, from Oxford Instruments in England and do spectroscopy. Well, Paul and I wanted to do imaging, and I remember we were sitting in the lab. At first we didn't have offices, we had desks. I said to Paul, well, you know, Paul, I don't know why they hired me. I guess you want to do spectroscopy, but I really want to do imaging. Paul said, oh, I want to do imaging too. So, and in the meantime, as we were, shifted around, we didn't have offices, we had to go several temporary offices, and when we got our permanent offices, one of my friends came in and said, wow, where did you get all that great furniture? And of course we had stolen it on the way. which is also another important thing for good researchers, is use other people's ideas. Okay, so finally we said, okay, Oxford was, the interesting thing about Oxford was they would always agree to do anything you asked. They had incredible risk takers. Unfortunately, it always took them much longer than they said. And I actually experienced this in graduate school. So in the meantime, we said, can we make an imager? So all right, so we got this resistive magnet, which is 0.15 Tesla, about 6 megahertz. So here's Paul standing next to it. And so we had to make gradient coils. So we used the, at that time, known design of gradient coils, which was a Maxwell pair for the Z gradient and Golay coils for the transverse gradients. And we put it all together, and here you can see, here's what it is. So these are the transverse gradients. These circular ones are the Maxwell pair, and then this little coppery thing is the RF coil. It's kind of a saddle coil, and then there are the capacitors for tuning it. Okay, so I stole this from Paul's ISMRM presentation. So Paul at first insisted on doing projection reconstruction. Of course, I was interested in spin work. And it turned out that projection reconstruction didn't work too well. First of all, it gave some really pretty abysmal images. And one of the problems was that because we didn't really know the fields, it assumes everything's projecting along straight lines, which it wasn't, that, like the back of the skull wouldn't quite close. So he gave up. So finally he was persuaded to give up on that, and we started making much better images. So we put this together, and we took it to the University of Pennsylvania in Philadelphia, which was about a 1-hour flight away. And I think my wife said I spent about half of the year in Philadelphia, keeping it going. So here's Reddington and me looking at some pictures. And so we were getting some pretty decent pictures, and there was a lot of good clinical research done on that machine. So in the meantime, Paul and I were patenting stuff like crazy. Here's some of them. Thick slab imaging, taking 3D, make the slab and then do this spin warp with phase encoding in 2 directions. Alternating RF pulses to get rid of imperfect 180s. Spin echo, we actually patented using the spin echo for imaging. Nobody had done that before. Selective volume method for spectroscopy by Paul. Primers and crushers to get rid of spurious signals. Chemical shift imaging. Multiple spin echoes imaging T2. And selective excitation for steady state free precession. So, and there were others. So we were we were writing patents and or patent disclosures, and they were patenting them. Okay, so then we had, remember I told you how publication was important. Our first really, really big publication battle. So this was over a paper that I had written, and it was comparing what was called inversion recovery to saturation recovery as two methods of imaging to see which was more efficient. And basically, there were arguments, you know, well, this one's more efficient than that one, so we analyzed it. Anyway, so the medical system didn't want us to publish this. Well, why not? They said, well, we think it's wrong. And if it isn't wrong, it will help the competition. So these were somewhat contradictory. So my boss, Reddington, said, he said, well, okay, you guys, you can pick one, and we'll argue about it, but I'm not going to argue about both. So finally, he came back and he said that he had won the argument, and we got to publish it. Well, not only did we have that, but when I sent it in, and this is one of the things that's good about publishing, is somebody said, you know, this was assuming you tilt the thing 90 degrees. Somebody said, well, what if you don't tilt the spins 90 degrees? And I said, oh no, this is going to wreck everything. But what happened was we discovered that you could tip it less and go faster, which is essentially flash imaging. So here we go, and it shows that we get the same quality. Basically, this shows you the quality of the image, and we get the same quality just by going faster and tipping less. And we had a big argument about that later, which we didn't actually do this. We didn't try it. I just wrote down this theory. So we had a big argument later, which we lost about the patent, but that's okay. Anyway, all right. So back to this question of why do we do publications? Okay. So first of all, publications serve as a record. Everybody knows that. You know, in fact, I find and this is, and you know, if you do something and then you look at it a few months later, it's like looking at something from another person. So what does it mean? I don't know. Unless you really write it out in English, you don't really know what it means. Okay, it advances the field. Okay, but what I want to emphasize that I think people don't talk about enough is that publication is quality control of science. Because first, it makes the writer think hard about your data, make sure it's consistent and correct. When you're writing it down, you say, wow, why did I do that? What does that mean? You know, sometimes you have new discoveries or understanding, and that happens. I'm just writing a paper, and we learned a lot, and actually it was really, really good. You get feedback from referees and your friends and your competitors who maybe aren't friends, and you know that if you're going to publish this or you're going to go to a meeting, you don't want to look stupid, right? You don't want people to say, hey, he's a fool, right? And also, managers can watch and figure out whether your stuff is any good. If you're a manager, you're not as knowledgeable as the scientists or engineers who are working for you, so that how do you tell whether it's good or not? Well, a lot of them just guess, or you know, everybody wants to promote their stuff, but this is an independent check. So that's why I think this is really important. Okay, so our boss often said, and this is the manager said things like, he called it stamp collecting. So what's stamp collecting? It means, you know, you say, oh, look at this, I got all these stamps, you know, and nobody cares. But that's even though he said that, and even though they kept saying that, they let us do it anyway, so that was okay. Okay, so finally our magnet arrived. You see now it's 1.5 Tesla, not 2, because the a superconducting magnet has superconducting wire that's joined to itself, and the joint has to be zero resistance. And it wasn't really, and the resistance gets messed up when you go to higher field. So it sort of worked at 1.5T. It really didn't work at 2T. Even at 1.5T, the field would go down at something like 200 hertz per hour. So in fact, they had a special winding that you would ramp up with a separate power supply at 200 hertz per hour every day. And of course, one of the things you have to be careful with magnets is that they attract other things. And so we had this is probably the heaviest thing that got sucked into this magnet, which was an 800-pound RF amplifier. I remember, in fact, in terms of the, this ramping up thing, one day I was standing in the room and Paul had been using it the whole day. And you were supposed to turn the knob down on the ramp thing when you shut it off at the end of the day. And he came rushing in, he had to go home and he switched it off and he said, "Oh shit," and he switched it on, quench. We had lots of quenches. It was interesting. Okay, so one of the things we wanted to do is, I knew about was how do we improve the gradients? Well, there was a graduate student at the University of Aberdeen, actually slightly before I got there, named Rob Sutherland. And I saw that he had developed this idea, and he had these distributed gradients. So I didn't actually have this thesis at the time. So I drew a picture on the blackboard for John Skank. I just sketched. I said, well, it's something like this, So he went off and with a mathematician from GE named Moyed Hussein developed the whole fingerprint gradient idea. So here was a patent on this concept. And we went ahead and so here's why it's important. So if you look at the transverse gradients, the Golay coils, okay, so these are lines of constant steps in field. Okay, so this is, in the middle, this is fine. So you're zero, you're going up here and down there, up, 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 uh-oh. See, right in here, it levels off and you start going down again. Well, that's only slightly more than halfway to the gradients. So that isn't very good. If you look at the fingerprint gradients, then you go all the way about 90% of the diameter of the gradient winding. So that is much better. So John also developed a distributed winding Z gradient, which is much more uniform, made out of wire. And then one of the things that I knew that Rob Sutherland had made his gradient by taking wire and actually scotch taping it onto a cylinder. So I said, well, wire is, has a lot of resistance. What would the pattern be if we take solid copper, a sheet, and instead we cut out a path so we have wide strips going around. So John went off, and the next day he came back and he said, well, it's the same pattern except it's the negative. So instead of having the lines being where the current flows, you have the gaps being where the current flows. So that was another patent we had there. So we call this current streamline method for coil construction. So here's the first one. We actually got it made. Not quite sure I remember. I think we had it all made at the R&D center. They had a good machine shop and so on. So by then, we had our 0.15 Tesla machine going, and people were getting interested. So they were saying, well, maybe we should try imaging, but we better turn the field down. Well, Paul didn't really want to turn the field down because he wanted to do spectroscopy, which was at the highest possible field he could do. So he actually made a coil and did some head imaging. And he modeled this coil after a small coil which was used by these two guys named Alderman and Grant from the University of Utah. So you can see it's the same thing, but it's scaled up a lot. And here are the images that were made, the first 1.5T head images. And they were actually made by John Skank and Howard Hart. In fact, one of it was good we had Howard Hart, and Alex Pines at University of California once said, hey, you got heart, you got bottomly, you practically have the whole person. So the interesting thing was people were saying, well, RF wouldn't penetrate, you couldn't do this, et cetera, but including one of Paul's papers kind of implied this. But anyway, look, there's no hole in the middle, it worked, right? So these were shown at 1982 RSNA meeting in Chicago. And I remember going there. This is always fun when you're doing things that people think are impossible. And so I said, well, we did these images 1.5 Tesla. And so he said, so one of my friends said, you mean 1.5 kilogauss? I said, no, which is 1/10 of that. I said 1.5 Tesla. So this completely froze the industry. So Walt Robb, who is head of medical systems, decided in consultation with Reddington, he didn't talk to any of the scientists, to make 1.5T product. Well, this was a problem. We didn't really know how to do this. We didn't know how to do the RF. So anyway, in the meantime, Paul led this group and published papers on this subject. So the person who really solved the RF problem was Cecil Hayes, and I knew Cecil for a long time. He was at Medical Systems because he and I were physics graduate students at Harvard. So here he is, in a young version. If you want to know what he looks like now, just remove the hair and make him a little bit fatter, like me. Anyway, so here I am with our thesis advisor, who was at a later time, who is one of the members of the Harvard group that discovered NMR, Robert Pound. And so here's the problem. If you're trying to make a large volume RF antenna, you have to make it big, and you have to make it, you want a transverse field. How do you do that? Okay, so the problem is, if you take a big piece of wire, then the wire has capacitance between various parts of itself, and capacitance to nearby structures, or just to the rest of the universe, okay? So for example, if you take, after I do the solution to this, discovered by Cecil, if you take a 50 centimeter diameter circle of wire and you try to resonate it, for example, put in 100 picofarads, it resonates at 15 megahertz, which says if you want to get it to 60 megahertz, which is where we're going, you have to reduce that by a factor of 16, which means you need 6 picofarads of capacitance. Well, can you do that? No, it's not going to work, because there are all these other few picofarad things, and that's going to ruin the whole thing. So the answer is, what you do is, if you know this, if you're electrical engineers, if you take 10 capacitors, each 60 picofarads, and you put them in series, the net capacitance is 6. Well, in this case, I have 8 of them at 6, which is, so what that does is, if you think of a current going around the whole thing from the input, if you just have one capacitor, you have a certain current, you have a voltage building up. If you have a bunch of capacitors, then each one, you have minus 1 over j omega c, or j over omega c. So that cancels out the reactance of the nearby inductance. And so that means that these capacitors are much bigger, and the current flows in the wire and not to the rest of the world. So the second thing is, and this will only be appreciated by physicists or maybe some electrical engineers who study this, is to use the concept of parallel wire transmission lines. So if you have a parallel wire transmission line, you have a certain wavelength, and you have depending on the frequency, and you have an electric field between the wires and magnetic field perpendicular. So if you could wrap this around a cylinder, you would have a perfectly transverse magnetic field. The problem here is that if you look at 64 megahertz, the wavelength is 5 meters, roughly, and so that's much bigger than the circumference of the cylinder. So what you can do, and Cecil figured this out, is you make a slow wave transmission line. So instead of having what you have here is, you have a certain inductance per unit length, and you have capacitance between these wires. Okay, so now you put in some real inductors and capacitors, and you can slow the wave down, so the wavelength is in effect shorter, and it's exactly the circumference of your cylinder. Or it turns out you can make a high-pass structure and have it looking like that. So Cecil also had the brilliant idea of connecting the ends together, so it then becomes a resonant structure. And for some reason, okay, so here's the paper we wrote on this, and so for some reason he decided to go on working on the low-pass thing, and I decided to work on the high-pass thing, and neither of us really remembers why, but we did. So here's a coil that we made in Schenectady to do the first body imaging, and you see, so this is a high-pass coil. So the capacitors are made out of circuit board, which you etch, and you have these little islands, so you can reconnect them and change the capacitor. And these inductors are simply pieces of plumber piping, 1/4-inch plumber piping. So with this kind of a structure, we made this body image, and which we showed at one of the magnetic resonance meetings. Okay, so the high pass has capacitors at the end, the low pass has capacitors along the runs. So it turned out, that the high pass turned out to be better, and I'll tell you why. This is sort of funny, is that when they started making the product, they made the low pass thing, and people were getting their arms burned. And so what happened was that when you put your arms, the coil was, you had a patient tube, and the coil was on the outside, and so people had their arms next to the capacitors where the electric fields were high. So the initial solution to this was to put cushions in so that people didn't have their arms next to it. But eventually they realized that it was really better to do this. In fact, Cecil figured that out, so they switched to our thing. So the other thing about the birdcage coil that's really great is that it has two orthogonal modes. So you can actually make it rotating field in quadrature. So what you do is you have one mode of uniform field this way and one this way. So you feed this with cosine omega t and this one with sine omega t, and you get a rotating field. Well, that's good because the spins only rotate in one direction, so that you actually save a factor of 2 in the power you're applying, and you gain a factor square root of 2 in the signal to noise ratio. So that was realized that there was a problem when we were using the linear excitation. There was a shading artifact, and so they called a big meeting in Milwaukee. So we had everybody there, and the boss walks in. Walt Robbins says, "Okay, so what are we going to do?" So they said, "Well, we need to do quadrature." So I said, "Okay, I think we can do it." They said, "Okay, how long is it going to take?" I said, "A week." And of course, they all thought that was funny, but we actually did it. So that was how we implemented that. So then you might want to know, how did NMR become MRI? Okay, so somehow the doctors and the industry got together. They didn't ask us, and they decided that we need to change this. We don't want the word nuclear, right? And so there was an editorial in Radiology by Dr. Meany. Yes, that was his name, Dr. Meany. And so Paul and I decided we were going to write a letter against this. Now, of course, being at GE, we were supposed to check everything we sent out with them before we did it. So, but we were saying, this is really nothing exactly to do with GE. Maybe, we'll talk to Reddington, and if he doesn't like it, we'll just send it from our house. So we went in and talked to him, and for some reason, he was mad at medical systems that day. So he said, "Oh, send it in, I don't care, just send it in." So, of course, we rushed back to our office and put it in an envelope with a stamp. That was the day when we didn't really have email and all this great stuff, and sent it in. And of course, Medical Systems was incredibly furious at this, but they were only mad at him because he had given us permission. So anyway, I think we wrote some good stuff here. It's like, one of Dr. Meany's principal arguments seems to be that he wishes to avoid the fears of the public over things nuclear. Isn't it time the public understands that our bodies and almost all matter on Earth are made up of atoms with atomic nuclei at their center, most of which are not about to explode or emit ionizing radiation? And Dr. Meany answers, "I applaud their call for an educational effort designed to overcome the fears of the public relating to things nuclear. This is an important responsibility for all in the medical and scientific disciplines. Pragmatically, however, it seems unlikely that in such an educational effort could be successful in the near term." Anyway, we lost. And it's probably good that it's MRI. I think that's okay. Oh, by the way, one of the arguments, this is really funny, is that the radiologists were afraid, because it was nuclear magnetic resonance, that the nuclear medicine people would take over. That's how childish it was. Anyway, shielded gradient. So we knew that, we turned on these gradients and there were these fields and they created eddy currents in the inside of the cryostat. So that was a problem. And these fields, the currents created fields interfere with imaging and so on. So Peter Romer, who really developed it at GE, came over one day and he had been trying to make an MRI system with a permanent magnet. But he said, well, one of the problems is that if you have a gradients inside, that the gradients will depolarize the permanent magnet material. So he invented this shielding method. So he showed it to us. So we then realized, wow, this would be really good for our regular superconducting magnets. I mean, permanent magnets really aren't good for MRI. Anyway, so he joined the group and developed it. And actually, there were two other developments. One was an MIT group who kind of bowed out of the picture, but they did it almost simultaneously in the University of Nottingham. So this was written up as a very nice patent with explicit instructions. So we got a little award from GE. So here we are, Pete and me. So one of the things interesting is this. So this inner tube is for the RF coil. This is the inner part of the shielded gradient, and that's the outer part. Notice there's air between it. So now that is completely filled with epoxy, right? So that cuts down on vibrations and other problems. So okay, so that's how that came to be. Okay, then we entered in. Okay, so we were doing 1.5T. We had what we came to call the field wars. And this is because we were at 64 megahertz, and there was a group at UC San Francisco, associated with a company named Diasonics, that was bought through a couple of things at 14.9 megahertz. Okay, so we were at 4 times that frequency. And they had all these theories that claimed that they had the optimum frequency. And not only did they have the optimum frequency, they made up a new term, the OF, right? The OF does this, the OF does that, and this is why this is the OF. So we had, the Magnetic Resonance Society, which was then SMRM, had these 2 big plenary sessions where we had arguments, and this was interesting. So I got up. So by the way, another thing that was really good was they were not checking our presentations ahead of time. So, nowadays everybody has to do things and you have to submit it and get everybody to sign off and all that stuff. No, somehow they didn't, which was good, right? So I got up and I had seen the presentation by the other guy, and I said, so I paraphrased his song. There's an American musical called Finian's Rainbow, where somebody sings a song that says, if I'm not near the girl I love the girl I'm near. So I said, if I don't have the field I love the field I have. In other words, okay, so they had that field, but didn't really mean it was the best, just because they liked it because they had it. So of course this got everybody laughing. And not only that, but I even talked to their boss, and he said, when we showed our body image, and they said, again, this was another great thing where you're doing something people think is impossible, and they said, is that cheating? Did you really do that? Yeah, we really did it. So that was fun. So then the next year we had another one. Okay, so this time they sent in their tougher guy, and so this time instead of, I counted, they were still talking about the OF. So I counted with, I said, a new concept called the PGF, the pretty good field. And I kind of borrowed this from Garrison Keillor, if you know his Prairie Home Companion, Ralph's Pretty Good Grocery. Doesn't really have everything, but it's still pretty good. So I said, okay, well, it does really well in imaging. We know you have to go to high fields for spectroscopy. It does well for that. So this is a good field, and it's really better than your lower field. And at the time, they compared their signal noise to ours, and it turned out they were comparing their head signal noise to our body. So yeah, but it turned out, so we were, in the end, we were right, and they decided this was too violent, and in fact, during the first one, Paul almost got into a fist fight with one of the guys. So in the end, we won. So we published this paper where we went and showed the signal to noise ratio going up. And after the first one, they liked what we did so much, they gave us these awards, right? So I got the Touche Award for saying, if you can't have the field you love, love the field you have. And here's Paul having a fight. So at the time, they used to have, actually, they had artists and people who could do stuff like that. That was good. So I have to mention also that there were really excellent scientists and engineers at medical systems. And here's some of the people that you know, and they've since gone to universities. Gary Glover, Norbert Pelk at Stanford, Cecil Hayes, University of Washington, Felix Worley at University of Pennsylvania, James McFall and Cecil Charles Duke, Erica Schneider at the Cleveland Clinic, and here's an engineer, Phillips at GE, and he's now in his own company. And they did a great job of implementing MR. They started, 18 months after we showed that first image, after we did it, they had a product, which is pretty amazing. Another important development was angiography that was led at our place by Charles Dumoulin and others, and lots of papers, and here's some nice pictures, and you've seen these kind of pictures before. And so another important thread was surface coil imaging. So at first, the problem was that if you took a surface coil and it was resonant, it would interact with the body coil. So what do you do about that? So we invented the blocking circuit that enabled you to use, at first people were trying to do it orthogonal to that transmit field, but of course our transmit field was rotating, so there was no orthogonal direction. So we made this blocking circuit, and we were able to make images. Here's an image of an eyeball with, you can see he's turned toward his nose, and this muscle is fat, and this muscle is thin, and that's the optic nerve, and that's the lens of the eye. So this was, made in, obviously Paul was the one sitting at the controls. This was Chris Hardy, and so this was made in 1983. So once we did that, then it occurred to me, well, what would be the right size coil? People were talking about it and sort of making things up and sort of approximating. So I said, well, so I did a little math, and I found out that the best coil was you would have to see, if you wanted to see a feature of depth Z, you should use a surface coil with diameter equal to that depth. So what happens if you make a more complicated coil? What if you make it with more turns? What if you make it with backward turns? So interestingly enough, what I found when I did all these little bits of math, that although each one of these configurations had different signal, different noise, the signal-noise ratio was always about the same, which puzzled me. So Pete Romer, who is a really, really good mathematician, did a calculation of an arbitrary current distribution using calculus of variations, and he found out that just a simple coil was 90% of the best thing you could get with a distributed current. So the bad news is that you couldn't do better with fancy coils. The good news is you didn't need to. So that was very useful result. Now, what about the phased array? So that was one of the next things. So Pete came to me and he said, could we have a matrix of coils where we have, where we somehow get different modes of circulation and figure out how to, so we can just look at the results from each little square, if you think of a matrix of squares. So we thought about it, and I couldn't really think of how to do this with more than 2 squares, so that wasn't very good. But I did think of, or remembered or something, the idea of having 2 coils. The problem is if you have coils and they're resonant, you bring them close together, they interact. So I thought of the idea of you overlap them and you get no mutual inductance. And also when you attach preamps, that would get rid of the interaction of the next nearest coils. So having started that, then Pete went on, took that and did a great job of figuring out all the details of how to do that, the math of how to combine images, and really a lot of, and what happens to the noise and so on. So anyway, we were working on this, and we asked medical systems, do they want it? You want this idea? He said, no, we don't want this idea. Well, could we present it at the SMRM meeting? No, we don't want it, but you can't present it. All right, next year. So we said, well, do you want it this year? No, we don't want it. Can we present it? No, you can't present it. But the patent was about to issue, so our boss said, yeah, you can present it, okay? So we sent in the abstract and it was rejected. So this was amazing. So this is the phased array. It was rejected. So I called up the guy who's in charge of the program, Truman Brown, who's a pretty wild guy. Said, Truman, you know, we have this other thing that was accepted, but we think this, the one we had that wasn't accepted is better. Do you mind if we just switch them? He said, whatever, I don't care. This was before the days when computers had their iron-fisted control of everything. So we did, and it was a big hit. And, you know, Pete went there, and basically people camped out around this poster because this was really one of the best things there. So here's kind of what it looks like, you know, or at least a drawing. So you see you have this overlap, so you get rid of the mutual inductance and therefore interaction between these two, and then the fact you're attaching these preamps, and Pete worked out the way to do this most effectively, really gets rid of the next nearest neighbor interaction. So so Pete also put them together. Here's the paper we wrote. Here's the actual things that we used first for looking at the back. And so each one takes a separate picture, and you put it together, and you get a really good picture. Here's one with an array of 10, two-dimensional thing. And of course, as you know, these have lots of applications today. Head coils, body coils, and parallel imaging. So here's a research group around 1990. Here's what it looks like. So some of the people, you can see there's Paul, a lot of hair and a beard, me with hair and a beard. And let's see, I don't know if you know anybody else. Well, Chris Hardy and John Skank, Peter Romer, and Otvar Mueller, who's a great electrical engineer. Okay, so there are really a lot of things I didn't really have time to discuss. You know, lots of spectroscopy, tracking by Chuck Dumoulin, where you could see things where they were going. A lot of development of MRI hardware, preamps, gradient amps, different RF parts. Image segmentation, image analysis, pulse sequence development, a lot of that was done by Gary Glover and other people at Medical Systems, and hardware and MRI system development there. Okay, so how did our inventions get into the product? So this is an important thing, because first of all, we had good communication, and we had good relationship between us and the GE Medical System scientists. But you couldn't just go and tell some engineer, say, hey, I've got a great idea, why don't you do this? No, they wouldn't do it, because they had their marching orders, they were doing their thing, they had enough work. We don't want to hear you have new invention. In fact, one of the managers at Medical Systems once wrote a letter and said, stop inventing things. I wish I had a copy of that, but he did say that. So what happened? So the way it actually worked, the only way it worked was, so we couldn't tell them, the scientists, so we would tell our managers would agree that it was a good idea. They would tell the other guys' managers, and they would tell them to do it. So you had to go up and over. That was the only way it worked. One other thing we did that was very effective was we had what they called readiness to serve. So if they had a really, really tough problem that they couldn't solve, say with RF coils, and they would invite the RF coil guys to go and talk to them. So that worked very well. So, okay, so what about this publications and so on? All right, so we had over this time, going from 1981, actually I put it up to 1994, which is when Paul left. We had, 8 to 10 PhDs, and we published a lot. Okay, so I just did a Web of Science search on these guys here. Okay, so this is, and no duplications, all right? So in those 14 years, we had 270 scientific papers in Web of Science with over 14,000 literature citations. We gave hundreds of contributed and invited talks at professional meetings and universities. 5 people actually got the International Society Gold Medal. And I, Paul, and Chuck Dumoulin were all on the boards of trustees and journal editors. So this is really good for GE, right? This is very successful for the company, very productive, and very satisfying for the scientists who are all able to get other jobs later. So here are the 5 gold medal winners, and fairly recently. Okay, so to summarize, MRI went from 0 in 1980 to $1 billion a year in 1990. So it grew as fast as Apple Computer. The R&D centers connecting and scientists at medical systems made many advances to MRI that gave GE a dominating market share, which was greater than 50% for a long time. And in addition to keeping GE in the lead, publication and participation in external technical meetings kept work at a high level, because again, you can't lie about things when you're going to be showing it to other competitors, and brought honor to GE and individual scientists. So here are some of the things we did. We ordered the magnet for spectroscopy, not imaging. So we made a low field imager, and Paul led image making at 1.5T, which froze the industry, and they made a product. Distributed current gradients, shielded gradients, bird cage coils, rotating fields, angiography, surface coil imaging, NMR phased array. There was a special GE system made for NMR guided therapy. Superconducting magnets. There was another group, a magnet group, that made magnets, and GE makes its own magnets. MR tracking and quiet technology that was done later after 1995, but that's an idea. So that's it. Thank you very much. I'm happy to answer any questions.
You
Right.
suggested that quite a few people there had nicknames. And I was wondering if you had a nickname there.
No. Apparently,
Are you
no,
sure?
it was just for some reason. Yeah, there was just, some of the youngish guys, at that time did have them, but mostly they didn't. But yeah, this was, if you wanted a nickname, I guess I would be Ed Edelstein, and maybe Paul would be Bottom.
That's on tape now.
Yeah,
So
maybe Bot.
I was going to ask, so I mean, it's amazing how many of the features of the scanners that we use that you've talked about in this, and I guess as sort of from the other side, I was going to ask, what was the thing that you spent the longest time working on that turned out to be completely worthless? Or did that happen, or did just all the ideas come through?
Okay, so what did I work on? Well, I actually once tried decontaminating ground by heating it with RF. And that turned out to be not a good idea. But but most of the things we did, I mean, were actually good. And basically, I've always said, well, here's a problem, let's work on it. We got to solve this problem. And luckily, we were able to solve the problem. I mean, it was partly that, it's partly, I don't know, good fortune, or the fact that we had this particular project. Like, I had no idea really how to solve the RF problem, but it was really solved by Cecil Hayes, luckily. Then once he did that, then I was able to do some stuff on that.
Are there other questions?
I have one question.
Yeah.
So you mentioned that one of the most important components is having a good research topic. What kind of, or the project itself?
Yeah.
What kind of advice do you have for junior researchers? How can we choose a good topic? Or do
Well,
we know?
it's very difficult to choose a topic. I don't know. It has to be a matter of judgment, and the main advice I have there is do a really good job on whatever it is, because if you do, because even this crazy project on heating the ground, actually we did get somewhere afterwards. The initial thing was no good, and then we did some other thing, heating the ground just using heaters, and that actually was good. So do a good job. The good thing about proving that wasn't a good idea was that there was this company who was telling GE they should decontaminate all their contaminated sites with RF heating. So, okay, they spent a couple of $1 million on us, but they could have spent $100 million getting these guys to do something dumb, right? So even that was worthwhile. So just, do your best, do a good job on it, and then find out, and then see, well, if this isn't good, is there some way we can go that is better? I mean, you often, sometimes you start out in some direction, and then you say, well, this isn't exactly right, we have to do this, we have to do that.
What do you think are some of your most useful patents versus your most trivial or silliest patents?
Well, the patents, okay, a question about patents. One of the things about the patents is the way these were used is basically GE held up its wad of patents, and the other guys held up their wad of patents, and they traded. So they didn't really, you know, but I mean, some of the things that were, I mean, most of those things that I talked about, where we patented things, those were, you know, important developments, and those were good patents, basically.
So did you patent anything that you think now is trivial?
Well, I patented something, I would say patent things that, you know, didn't work out, like the beginning, if you remember, we had this, okay, if we go back to the beginning, it's not exactly trivial, but it didn't turn out to be very useful, was we patented the idea of having the shielded room, but not having a shielded room, but rather having a little room attached to the magnet, see? And then the thing over the top. Well, nobody does that. I mean, there's always stuff like that. And they're all expired, by the way. You get about 20 years.
Okay, if there's no further questions, please join me in thanking Bill for a fantastic day.